This is on, right? Maybe they will add more power if it's needed. So I'm pleased to be re-invited to HighLoad. I was also here last year. I feel very privileged that I have 2 talks, and I wonder if it's because I am popular or because of MongoDB is popular. But this is certainly a nice conference to visit. So the first talk that we have now is about MongoDB replication. I have also, with some other databases, been always very interested in high availability and replication algorithms. So I have been involved a little bit now in improving MongoDB replication. That you will see in 3.2. MongoDB 3.2 is currently a release candidate, so you can go and download it. But we actually haven't kind of announced it. Of course, it's open source, so what is there is not a secret. But you will hear more about it, I think, in the near future, also from other people than me. So my name is Henrik Ingo. I live in Helsinki, or a small town outside of Helsinki called Järvenpää. The English translation for that would be the end of the lake. So there is actually a lake that is quite narrow, and at the end there is this city called the end of the lake. And I work as a MongoDB solution architect, so I don't actually write MongoDB code itself, but I help our customers in Northern Europe to build applications on MongoDB. Let's see what happens here. So today I will talk about what we have done for MongoDB 3.2, and it's actually based on some academic paper. So there are words here like consensus and state machine, and then we will talk about how replication works in MongoDB today, and what are the improvements we have taken to MongoDB 3.2. So the first question, of course, is why do we need replication? To propose a solution, we need to have some requirements that we are trying to meet. And of course, the kind of obvious reason is that we want high availability. Right? So for any part of your solution stack, of course, high availability means if one server breaks, I have an extra server waiting to take over. So that is redundancy. But with databases, of course, the problem is that it doesn't help that I have one extra MongoDB server somewhere. It should actually have the exact same database that was on the lost. So I don't want to lose the state. I think Bruce mentioned this in the morning talk, that doing this for a web server or something is easy because there is no active state that they need to keep typically. So just having a bunch of servers is an easy solution. With databases, we end up doing replication to make sure that we have redundant copies of the most recent database state. The other reason has to do with performance more than high availability. So you might want to have copies of your data in multiple places of the world. It turns out that speed of light is actually a significant constraint on your performance if you have an application with a global user base. So, for example, here in Moscow, let's say, if you have a company here in Moscow and the servers are here, but you also have American users maybe in San Francisco, I don't know, maybe somebody here has actually measured it, but just knowing what the distance is from Helsinki, probably we are talking about 150, 200 milliseconds round trip from Moscow to San Francisco. Is that correct? Or is it more? Maybe 200, 300. On the other hand, a MongoDB query can be less than 1 millisecond. So now if you want your page to load as fast as possible to your users, you can optimize the MongoDB query as much as you want. It's already super fast when just the network round trip is hundreds of milliseconds. So the solution, of course, is to use replications. You have copies of the database itself on every continent of the world. Of course, if you use public clouds like Amazon or something else, this is very easy to do nowadays. Any startup that has a credit card can easily have servers on 3 or 4 or 5 continents. So consensus is actually an academic word. I will, on a future slide, refer to the academic paper about the Raft algorithm. So this is why we now have a bit of academic language in this talk. Consensus basically means that I have multiple database servers and I want them to be in the same state. So in a way, consensus is actually what we normally call replication. We also talk about state machine. This is the academic version of saying database. So it's essentially the same thing. So when we say, when we are solving a problem of consensus for state machines, we are essentially talking about database replication. Now, for high availability, it's kind of a fun problem. Most other problems in software engineering are kind of well defined. So if I have a query, I want to make it faster, maybe I add a better index and then I can measure how much faster it was. And I would expect that all future queries then will also use this index and they will be equally fast with some variation, of course. Now with high availability, the problem is that we are trying to build a system to survive failures. And it is very difficult to know in advance which failures will happen out in production. So that's kind of fun to test. You can be very inventive if you are testing high availability systems. So an easy test maybe is you shut down the MongoDB process, but more fun might be if you go to the electricity plug and you just unplug the electricity from the server and see what happens. Or you can play with firewalls and create bad network routing or bad firewall rules to see how will the system survive when the network isn't working as you would expect. Another interesting failure is everything is working fine, but on one server the clock is different than on the other ones. So there is an endless amount of failures that could happen. And of course the problem is that whatever we have tested is not what will then actually happen when something goes wrong in production. But we can try to be as robust as possible. So the idea of consensus is kind of simple. We have 3 servers on this picture, and they have some state in the database. And they need to be the same. So that's what we are trying to achieve. So on a high level, how we actually make that happen is a separate question, but this is what we are trying to achieve. So this could be quite difficult if you think about it as a generic problem, because you could have a large amount of servers and they would all need to agree on the same state. So a common subset of consensus protocols is so-called leader-based consensus. This is what we have in MongoDB as well. And it simplifies this problem by saying that, okay, when clients update records in the database, we actually have to select a single server. So in a way, we go back to the original model where we have a single server with a single database and all updates happen there. And all the other servers will simply then follow this leader. and do the same update. So this where there is no ambiguity, for example, with locking records if two clients try to update the same record, because we know that the leader is in charge. So leader-based consensus, again, is academic language. In MongoDB replication, we talk about primary server and secondary server. I have a history as a MySQL expert, where they are called master server and slave server, but now I work for an American company, and this is apparently politically incorrect in the US. So we talk about primary and secondary. It's the same thing. So how does this work in MongoDB? So elections. And now we will use current MongoDB as an example. So in leader-based consensus, the replication itself is simple, right? So everything, all updates happen on a single server, just as they would if you are not using replication. And then the other nodes copy these operations. Now I think we have missed these arrows that again, academic papers use in describing state machines, and they are now small boxes instead. But anyway, you have some operations. You set a column or a record to a new value. So this is very simple. But of course, the question is, how do we know which node is the leader? Maybe in the beginning we know which one it is, but then the failure happens. This is why we have high availability solution. And the leader is gone. So the question is, where will we now do updates when the node is not there anymore? So in the solution to this is to have an election, kind of like in the real world also. So one of the nodes will typically become a candidate, that I want to be the next leader, and how this exactly happens is interesting, but I will not go into so much detail on that. And then the other nodes will look at this and say, depending in MongoDB, it depends on a few things. For example, we only approve a leader that actually has a recent view of the state machine or the database. So sometimes with replication, it happens that some servers can fall behind. That would not be a good leader, because if we need to follow this server, we would have to go back in time and lose some transactions. So we prefer a leader that is current compared to the rest of the cluster. So there are some heuristics like this that influence who will win a MongoDB election. But this way we have a new primary server, and the others can again follow this one, and clients can do updates on this one. So this election is an interesting part of replication. Replication itself is kind of easy to understand when you have this kind of leader-based or what we would say single master replication. Because you just kind of replay something that happened on a single server. Elections are interesting because that's when the failure actually happened, right? So this is when some server crashed and we need to get back into a functioning state. And this is kind of a crucial point in time where things can also go wrong if our high availability solution is not robust. So some key requirements for this is that, well, there must be exactly one leader at any time. This is the point of using a leader-based approach or a single master approach. So how do we ensure this? And what would happen if this was not the case? So what if in this selection actually two nodes at the same time say that, oh, I want to be a leader and I also want to be a leader, and somehow they decide that, yes, I will now start doing updates because I'm the leader. This would be a situation we call split brain. So actually we would now have two halves of the database that would start diverging because they would process different updates from different clients. Can be difficult or impossible to recover from. So we definitely do not want that to happen. It's essentially database corruption if that happens. So to prevent split brain, we must ensure that there can only be one winner in this election. And this is why we use majority elections. So mathematical concept of majority is very nice. You can only have one majority. So this means if a majority of the other servers have voted for the same leader, we know that there cannot at the same time be another leader somewhere else. So everybody else will only have minority support. When you are designing clusters, surprisingly difficult for people to understand that 50% is not the majority. So if you have two servers, you might think you have high availability, but if one server votes for itself and the other server votes for itself, they both have 50%. Neither of them can become a leader, right? Because they don't have a majority. So, so this is why you need to have, for example, in MongoDB, at least 3 nodes in a replica set, so that you don't have, so that you actually end up with winners in case of a network split, for example. Another part that you might forget, it's kind of obvious, is that the old leader that has been the leader for a while must know to step down at the right time. So if we have elected a new leader, that means also the old leader can no longer continue to process updates. Otherwise, we would again have a split brain. The reason this might be difficult to remember is that the first failure we think about that the old leader has crashed. So it's kind of gone and we need a new leader. That's one possible failure that can happen. But there are all kinds of failures. So what can also happen is that the leader is there, but it is disconnected from, like, the network to the other servers isn't working. And it's disconnected. So it might still think it's the leader, but nobody is actually replicating updates from it anymore. And again, we are risking to have split brain. So part of an election typically means if the leader notices that it's no longer connected, again, to a majority of the other servers, it must step down and no longer cease to be a leader. This is actually different from real-world democracy, where if you vote for some candidate to be a leader, I think in Russia it's even 7 years. In Finland, the presidency it's 6 years. If after the election you regret that who you have chosen, they will still continue for the whole term. You cannot change your mind after this. But in MongoDB replication, the leader must continuously receive support from the majority. And if he is disconnected from a majority of the cluster, he must step down and cease to be the leader. So, for 3.2, which is now in release candidate, so you can actually try this if you go and download the release candidate version of MongoDB. We have done several improvements to our replication and especially the election protocol. And well, I will talk through them on the coming slides. Why did we do this? One was to decrease failover time. Previously, MongoDB heartbeats were very hardwired to a 2-second cycle, and there were other reasons why elections could even take quite a long time. And then similarly, this we want to detect faster that this old leader has to cease to be a leader, so that we avoid situations where we have some small amount of time where we have 2 primaries, the old one and the new one. So this work is actually now based on an academic paper describing an algorithm called Raft. If you think this word is familiar, a raft is a floating device, like not a boat, but maybe if a ship has sunk, you might build a raft of some pieces of wood or I don't know, some other things that float. This would be a raft. It is written by Diego Ongaro in Stanford University. And we chose this because, so this is quite a new algorithm. I think there were a couple of papers released, but his thesis was from last winter, I think, which describes kind of the full current version of Raft algorithm. And it happens to be very similar to the existing replication in MongoDB, which is, of course, we have developed several years ago. So the benefit of this, though, is that in the academic world, you have more people actually reviewing this algorithm, and they even write proofs of correctness to say that this algorithm will work correctly in all possible situations. So it turns out actually in the current MongoDB replication, I can think of some corner cases where the elections are not guaranteed to work as they should. So we definitely want to benefit from Raft algorithm to make sure that our replication is as good as this academic algorithm. Raft itself, in the academic world, often these replication algorithms or consensus algorithm, as they would say, the king in that world is an algorithm called Paxos. Everybody, even in my work at MongoDB, will ask often that is the MongoDB algorithm based on Paxos? So no. In fact, I have never seen a real world, or at least not an open source implementation of Paxos that was good to use. But in the academic world, this is one of the first ones, and it has proven to be correct. But it's very difficult to understand, so no developer actually can create a good implementation of Paxos, even though in theory it is a very good algorithm. So the nice property of Raft as an algorithm is actually easy to understand. So I believe most people here could read it and understand at least half of what it's doing. And I have read it like 3 times, so I'm starting to understand more than half. From that point of view, it's kind of more relevant to actual real-world software. And there are a lot of databases using this already, even though it's only 1 year old. So it would be wrong to say that MongoDB 3.2 is a Raft implementation. We have simply made slight modifications to our earlier replication protocol. There are a lot of fundamental differences. For example, in the Raft algorithm, it is the leader that will connect to all the secondaries and push updates to them or send updates to them. Whereas in MongoDB, it is actually the secondaries that connect to the primary server and read changes from the Uplog and then apply them to themselves. So it's actually completely inverted. But that doesn't matter. On a high level, actually, you need to do the same things. So we have been able to look at Raft and identified some things that we didn't have before. And we actually now are copying them into our replication, even though our replication is fundamentally still very different from Raft. So these 3 things I will talk about. The first and I would say most important improvement is the introduction of something called an election term, which in Raft is just an ID. So when the cluster starts, you first need to select one leader, and this will be the first election term. So you have ID number 1. And then each time the primary changes, or even if it doesn't, so you might have elections where, for example, the result is tied, or there is no leader chosen for one election. So each time you have an election, you increase this ID. This means that you when nodes participate in voting, it's clear which election they are voting in, and this way you can ensure that you only vote once in each election. Again, otherwise this concept of majority breaks down if you first vote for somebody and then you change your mind and also vote for somebody else. In current MongoDB, we have tried to protect against this, but we didn't have this concept of a term ID. So in the current MongoDB algorithm, actually you have a limitation that you can only give one vote every 30 seconds. And this is based on the idea that we have this kind of 2-second cycle where things happen. So a typical election will happen in like 2 seconds or 4 seconds. And that's why if you wait for 30 seconds, you kind of know that whatever happened in the previous election is surely over, and now I can vote again in a new election. But we didn't have this ID to actually distinguish the elections from each other. It was purely based on waiting enough time. And this is of course unfortunate. So it could happen that the primary server goes down, and then the remaining nodes have an election, and this somehow results in a tie. This could happen just based on kind of statistics, so and network topology, and if you end up with a tie, you have no leader, but you also cannot do anything anymore because now all nodes are waiting for 30 seconds before they can vote again. So this means failover time could be over 30 seconds sometimes in current MongoDB. So most of the time it would be faster, like 4 seconds, for example. You do an election and you have a new leader, and then it's done. But sometimes if you are unlucky, you would have to wait 30 seconds, or why not 60 seconds if there is another tie. It's unlikely, but it could happen. Now in MongoDB 3.2, if you use the new election protocol, when there is a tie, the nodes will see that, okay, we didn't get the new leader, and somebody can immediately start a new election because we can distinguish it from the old election. So we can immediately have new votes without a risk for breaking down this counting the majority. Yes, so again, the academic term for what this term ID actually is, it's a logical clock. So actually it's the same thing as waiting 30 seconds, except that you don't need to wait for the physical time. It's actually a logical counter that distinguishes how time proceeds forward. This is a slide with actual MongoDB data. So this is how MongoDB Uplog looks currently. How many, I suppose there are some MongoDB users. How many of you have actually seen this before? Okay. Not almost half, I would say, but not quite. So this is what you are familiar with. And in current MongoDB, you actually have two independent things that identify a transaction. The kind of logical identification is the field TS, which is a timestamp. And then you have the field age, which is a hash. And then if you look downward, there is the transaction that was actually recorded. So in this case, for the OP field, we see there is an I, so this means there has been an insert to the collection called test.nullTest. And then the object that was inserted was ID 3, and the field A with the value of 3. That's on the bottom. So anyway, I don't really care about the payload in this case, but for the replication and election, we care about the TS and H fields. TS already uniquely identifies the transaction. It's a combination of the current millisecond in time on the primary server and the counter, which means if we have multiple transactions in the same millisecond, this counter will increase, so they are different for each operation. The age field is essentially a random number. In different versions of MongoDB, it was generated in different ways, but you can think of it as a random number. And this is essentially a global transaction ID. So it could happen, for example, before and after a failover or for other weird reasons. Maybe you could have two servers where on the same millisecond you had one operation which would then have the counter 1. So they would look the same, but the age field would actually be different because it's a random number. So this is how you would separate that these two are not actually the same transactions. So the age field is used around the failover for servers to go back in each of their uplog to make sure that they start from a common point and then go forward again. Now in MongoDB 3.2, we have basically added this concept of a Raft election term. So we have added, and this is the middle green box there, we have added a field called T, which is the Raft term. So in this slide, it seems like I have had 42 elections in the past. I am now in term 42. In addition, we have reused the field that was already there. So from the second number in the TS field is now the Raft counter. So you see that instead of a low number like 1, it's 861. It doesn't mean that I had 861 transactions in the same millisecond. Rather, there have been 861 transactions since this primary was elected, which is primary number 42. Okay? So we used the same slot for data, but it actually means something different now. In addition, you still have the milliseconds there. They actually are not used by the Raft protocol anymore. So to uniquely distinguish a Raft transaction, you would take field T plus the latter part of TS and ignore the millisecond. But it's kind of nice to know at what time the transaction happened. In addition, this field H is still useful. Raft doesn't actually specify a similar mechanism, but it's still good to have this kind of hash of a transaction. Because again, of course, on some other server, you might also have transaction number 42 plus 861 or 860, and it would look like they are the same, although it might be a completely different database. But this random hash will, of course, always uniquely identify transactions. Whoa. There we go. So the second change has to do with heartbeating. In current MongoDB, there is a separate heartbeat thread on every server that connects all the other servers, and they send heartbeats to each other every 2 seconds. And of course, this doesn't scale well. So if you would have hundreds of servers in a replica set, some users want to do that. You would have like, I don't know, millions or hundreds of thousands of heartbeats going across to each other. So you might see significant kind of CPU and network traffic purely from the heartbeat. That doesn't make sense. So this is why it's limited. First of all, the interval is 2 seconds. It's quite long. That means when MongoDB primary fails, it will take 2 seconds before all of the nodes even realizes this. So this is actually quite a long time for somebody that cares about uptime. You might want this to happen in less than a second. The other thing, what we have done is we have actually limited the number of nodes. So even today, you can still only have 12 voting nodes, but you can have more nodes that don't participate in elections, up to 50 nodes in a replica set. I have also, because I kind of play with this more than other people, so sometimes I have also seen odd behaviors with so-called asymmetric network partitions. So it might be that between 2 nodes, the heartbeat thread cannot connect from this server to this server, so it considers that this server is dead. But actually the replication, well, if this is the primary, then this server can actually connect this way, because you might have configured the firewall, for example, that traffic only goes one way, which is usually a bad thing to do, but it's completely possible to do it. So now this secondary could still successfully connect and replicate from the primary. So actually everything is working well, but the heartbeat thread would think that something's wrong and something needs to be done. I suppose the worst case is if the opposite happens, which also have happened, that everything is not working well, but the heartbeat thread thinks that everything looks fine, because the heartbeat thread has its own reality compared to how replication is actually working. So in Raft and in MongoDB 3.2, heartbeat and replication is the same thing, right? So even if there is, so you only have one thread that is doing the replication, and as long as you get some response from the primary when you are reading operations from the uplog, this counts as a heartbeat. So this of course means even if there are no updates to replicate, we need to have kind of a no-op just for heartbeat purposes, so that the secondary and primary connects with each other. So this is good. It also means that the heartbeat thing is now from secondaries to primaries. So not all nodes need to send heartbeats to each other. So this means we can do it more frequently. And on the other hand, there is no overhead because we would be doing the replication anyway. That's the whole point of what we are trying to do. MongoDB also, since some versions ago, supports chained replication. So this has, again, the benefit that now heartbeating will follow this same topology. So the point of chained replication is, for example, if I have some servers here in Europe and some other servers in the US, it would be kind of costly for all the US-based servers to connect to a primary that's in Europe. So instead, MongoDB, you can configure this, but actually automatically it should figure out that it only makes sense for one US-based server to get the uplog from Europe, and then the other servers that are close to it, maybe in the same data center, will chain behind that one. So this optimizes the network traffic. Now, again, when we use this chaining with the old heartbeating, it could happen that the server that's behind there might not be able to directly connect to the primary. So heartbeating wouldn't work, even though it's actually getting replication events from the other server that's also in its same data center. So now when heartbeating and replication are the same thing, there is no inconsistency here. So if I can replicate by chaining to another node, also heartbeats will be sent this way. And finally, with these robustness improvements, we have made the timeout, the heartbeat timeout configurable, or in Raft it's called election timeout. So no longer is it a fixed 2-second interval, rather you can choose what the timeout should be. And this is a good thing. Another thing actually in current MongoDB, you had different timeouts. So if you have an unresponsive network, the network timeout would be 10 seconds. Whereas for some other failure cases, if the primary has crashed, you might immediately do an election within the next 2-second cycle. So depending on what type of failure, the reaction time would be either 2 seconds or 10 seconds. In Raft now, we don't care about what failure happened. If we reach this timeout for whatever reason, then it's time to have an election. So it's much more consistent and predictable, and it's also configurable. The reason this needs to be configurable is, of course, simple. If you have a cluster spanning over long network distances, the timeout should be long. Again, between Moscow, China, Australia, South America, North America, we are talking about network round trips of many hundred milliseconds. So of course the election timeout cannot be shorter, because then we would have elections all the time when the nodes are simply trying to connect to each other. Whereas if you have if you have a cluster in a single data center with a good quality network, the network timeout is a few milliseconds. So you might actually have an election. The network round trip is a few milliseconds. So you might actually have election timeout less than a second and be completely fine. And those that want maximize their high availability want to minimize the failover time. There are some other things in the new protocol. So in addition to this configurable timeout, there is actually a small random component. This is because we don't want all the nodes to become candidates at the same time. Rather, we would actually want one of the nodes to go first, and then the others receive the invitation to an election from this node and vote for him. And that way we immediately get one winner rather than getting a tied vote or many minorities. So altogether, elections now happen faster, and the speed is configurable, and you are more likely to have a winner at the first election. So what have we talked about? In MongoDB 3.2, we have taken inspiration from an academic algorithm called Raft, and basically we have copied 3 things from it: the term, different style of heartbeating, and a configurable election timeout. And with this, we want to achieve a much faster failovers and faster detection of errors. Also, more control to prevent spurious failovers. So that means if you have a very bad network, you can increase the timeout to be more resilient to failovers, to failures. And also, this fixes some corner cases which maybe were not correctly handled by MongoDB until now. So this hopefully will bring you your MongoDB clusters even better uptimes in the future. Thank you. I don't know if we should take questions or should we go to it?
Sorry for interrupting you, but it's time for questions already. Okay?
Yes, I am finished.
Окей, какие вопросы, прежде чем прерваться, давайте несколько вопросов, пожалуйста.
Hi. So the question is about performance. So how this Raft algorithm affect performance compared to the normal master-slave asynchronous replication?
Yeah. So actually the performance is the same. So the replication of events is the same as before. So it doesn't affect the performance. It more affects the fail. When you actually have a failure, the failover is faster. So maybe from that point of view, performance is better because you can continue writing to the database faster than before.
Right, but as far as I know, this is asynchronous replication. So you have to, for example, this is asynchronous.
No. So this again, like we didn't fundamentally change our replication protocol. I think if you read the Raft paper, you could say that it's kind of synchronous replication, but MongoDB still is the same as before. Okay, so strictly speaking, if you are familiar with MongoDB, we have these different write concerns, and if you use write concern majority, then the MongoDB experience is kind of the same as Raft, and it's kind of synchronous replication. However, under the hood, we are still asynchronous. So if you don't use write concern majority, it's actually not like Raft. But the elections are like Raft and more robust than before.
Okay, thank you.
Yeah.
Так, прежде чем Путин, еще вопросы, пожалуйста.